Hi dear students, in the last class we discussed the growth of the current in an LR circuit, and today we discuss the decay of current in an LR circuit. We have the circuit, resistance R, inductor L, the voltage applied is E, and this is a key. A current I is flowing through the circuit. When the key is switched on, when the key is pressed or when the key is closed, the current starts to flow through the circuit, and after a certain time, as current becomes the maximum, and now a steady current, they say that current is I0 is flowing through the circuit. If the key is opened, that is, the key is opened, now the circuit is broken. Is here circuit is broken, then the steady current which was flowing through this circuit starts to decay or starts to decrease. When steady current flows through the circuit, no EMF will be induced across the inductor because di by dt is equal to 0, since the current that is flowing through the current was not a time vary one, that was a steady one. But when the circuit is broken, the current starts to decrease. There will be a change in the value of the current with respect to time. Then an induced EMF that again developed in the inductance L. That is, this induced EMF slows down the rate of decay of the current. അതായത് ഒരു കോൺസ്റ്റന്റ് കറണ്ട് അതിൽ കൂടി ഇങ്ങനെ ഫ്ലോ ചെയ്തുകൊണ്ടിരിക്കുകയായിരുന്നു സർക്യൂട്ടിൽ കൂടി. പെട്ടെന്ന് അതിൻ്റെ മാഗ്നിറ്റ്യൂഡ് മാക്സിമത്തിൽ നിന്നും സീറോയിലേക്ക് കുറയുമ്പോൾ ആ ഡിക്രീസിനെ ഓപ്പോസ് ചെയ്യുന്ന രൂപത്തിൽ ഒരു ഇൻഡ്യൂസ്ഡ് EMF നമ്മുടെ ഇൻഡക്ടർ കോയിലിൽ ഡെവലപ്പ് ചെയ്യും. ആ ഇൻഡ്യൂസ്ഡ് EMFന്റെ എന്തിനാണ് ഡെവലപ്പ് ചെയ്യുന്നത്? That induced EMF tries to oppose or tries to slow down the rate of decay of the current. കറണ്ടിനെ കുറയാതിരിക്കാൻ വേണ്ടിയിട്ടുള്ളൊരു ശ്രമം നടത്താൻ വേണ്ടിയിട്ട് അതിനാണ് നമ്മുടെ ഇൻഡ്യൂസ്ഡ് EMFത്തിൽ ഡെവലപ്പ് ചെയ്യുന്നത്. Let me note down here, that is, when the circuit is broken, that is, the key is opened, an induced EMF is dl by dt, the dt is again produced in the inductance L, and this induced EMF, it slows down the rate of decay of the current in the circuit. That is, I can mention here like this shortly, that is, when the circuit is broken, the EMF, that is, the voltage in the circuit, that goes to 0. When the circuit is broken, the voltage that applied becomes to 0, and we know the expression for the voltage that we have already written in the last class. That was IR plus L di by dt. That is, the voltage across this resistance is IR, the voltage across this inductor in the figure, that is L di by dt. Voltage was distributed across the resistance R and across the inductance L. That voltage, this expression here, that will goes to 0, then you can write this is 0 is equal to IR plus L di by dt. Or I can write this equation, L di by dt is equal to minus IR. If I bring the I to the left side, this will be di by I, that is equal to minus R by L. I bring the dt right side, dt, or if I do the integration, that is this will be natural log I, that is equal to minus R by L t plus C. Now to find out the constant of integration, that is C, we have to put the initial conditions. Initial condition was time t is equal to 0. The current flowing through the circuit was the maximum current, the steady current I0. Then apply this initial condition to this expression, that is when t is equal to 0, I is equal to I0. Therefore, this will be natural log, instead of small I, you can substitute this capital I0. This steady current natural log I0. Then at time t is equal to 0, this t is equals to 0. Therefore, the first time is 0, then t is equal to C. The value of C is nothing but natural log I0. Again, substitute this value to this expression. Therefore, the final expression that we can write this is a natural log I is equal to minus R by L by T plus natural log I0. That is, if I bring the natural log this I0 left hand side, then this will be natural log I0 is equal to minus R by LT. If I integrate, natural log disappears. This will be I by I0. Then right hand side will be minus R by L T. Okay. Then current I can be written as I0 e power minus R by L T. This is the decay of the current in R in a LR circuit, or we can say this is the current decay in LR circuit. Here we define the term, that is tau is equal to L by R. This is nothing but the relaxation time. Then I am going to put T is equal to tau in this expression. Therefore, the equation will become I is equal to I0 e power minus 1. Or before that, for your convenience, I will write this is as I is equal to I0 e power, if tau is equal to L by R, then this will be T by tau. Then I put T is equal to tau. When I put T is equal to tau, this will be T by tau. Then we will get e power minus 1. Fine. And this is equal to e power minus 1 is nothing but, or e power 1 by e is nothing but 2.718, that is equal to 0.3679 I0. Or we can write this I is equal to 0.3679 I0. Thus, the relaxation time, that is this tau, is defined as the time required for the current to fall to 36.79 of its maximum value I0. That is, one can write this is in this way: I is equal to 36.79% of I0. Thus, relaxation time we can write in words. Okay, the relaxation time is defined as the time required for the current to fall 36.79% of its maximum value. Now I want to plot this equation, that is I is equal to I0 e power minus t by tau. I copy that equation here. That is, when t is equal to infinity, when the time goes to infinity, what will be this I? This I is equal to I0 e power minus t by tau, means that t goes to infinity. This will be the minus infinity. Minus infinity is equal to e power minus infinity equals 0. Therefore, this is equal to 0. It means theoretically the current decays to 0 only after infinite time. Actually, practically, the L by R, because the inductance that will be in millihenry and the resistance that will be in kilo ohm, that is, the value of L is smaller and the value of L is larger. Therefore, this quantity L by R, that will be defined as the relaxation time, that will be smaller. Therefore, the L by R is smaller, means this is nothing but the relaxation time tau, that is, the tau will be smaller. Then if you look back to this expression, that is, here the tau is smaller, then the term t by tau will be large. If t by tau is large, I mean if it tends to infinity, then e power minus infinity will come, that is equal to 0. That is, the current, if e power minus infinity is equal to 0 means, then according to this expression, the current I will goes to 0. That is, the current falls to 0 in a fraction of seconds. But theoretically, what we have seen here, when the time tends to infinity, that is here, when the time tends to infinity, I is equal to I0 e power minus infinity will come according to this expression. That is, the current decays to 0 only after infinite time. But practically, because of this ratio is smaller, the current falls to 0 in a fraction of seconds. Okay. Now, what will be the problem if the current falls to 0 in a fraction of seconds? That is, I will discuss later. Now, let us draw the picture of the decay of the current. It is nothing but the graph of this equation. This I is equal to I0 e power minus t by tau. We need the x and y data. That is, the x-axis we have the time. When time it is equal to tau, then I is equal to I0 e power t by tau. That is, tau by tau will be minus 1. This value just now we have seen 0.3679 I0, and when time t is equal to 2 tau, this will become I0 into e power minus 2, 0.1035, something like that, I0. When time t is equal to 3 tau, this is current I will become I0 e power minus 3. Then again this value reduces, this 0.0550. So on, if time t tends to infinity, our I is equal to I0 e power minus infinity, that is I0 into 0, because e power minus infinity is equal to 0. This will become, this value goes to 0. That is, if the time increases, see that the value also decreases. Therefore, this is a decaying graph, because this exponential is a e power minus x, that is negative decay. Here we have to plot x and y. The x-axis we have time t is equal to millisecond. On the y-axis we have the current, that is, here the maximum value of the current is nothing but I0. Then the points, that is, we have 1 tau, 2 tau, 3 tau, 4 tau, goes on. When time t is equal to tau, that is time t is equal to 1 tau, that is, the current is the maximum. Current is the maximum means current decreased from the maximum to the 0.3679. That is, if it is the I0 here, then this will be the 0.5 of I0. Then just below that, this may be the 0.03, 0.3679. Then approximately our graph first point will be here. Then when time t is equal to 2 tau, this again 0.1. 0.1 may be somewhere else here, and next to 0.05, time t is equal to 3 tau, like this. That is, this is a maximum value from where the graph decreases. The graph will be approximately like a, should be a smooth one. This is the decaying of the current in an LR circuit. Okay, fine. Now let us come back to this problem. That is, practically, when the current falls to 0 in a fraction of a second, what will be the consequence of this problem in the circuit? That is, the picture, this is our key. The constant current was, that is, I0 was flowing through the circuit. Then immediately the key is opened. That is, the circuit is now broken. The circuit is broken means a huge amount of resistance, that is, an infinite resistance is introduced in the circuit. Or we can say at the time of breaking the circuit, the resistance of the circuit become infinite. That is, the resistance of the circuit become infinite means the relaxation time tau is equal to L by R. If the R is very large, then this term, that is the ratio L by R, that is a relaxation, the tau will be very small and tends to 0. There's a rapid decay of the current. Relaxation time is very small means immediately the current goes to 0. Thus, this rapid decay of current results in the large induced EMF across the inductor. അപ്പോൾ വളരെ പെട്ടെന്ന് ഇതിൽ ഒഴുകിക്കൊണ്ടിരിക്കുന്ന കറണ്ട് പെട്ടെന്ന് കുറഞ്ഞ് കറണ്ട് സീറോയിലേക്ക് വരുമ്പോൾ ഈ ഇൻഡക്ടർ ശ്രമിക്കുക അതിലൂടെ അതേ കറണ്ട് മെയിൻറ്റെയിൻ ചെയ്യാനാണ് ശ്രമിക്കുക. അപ്പോൾ ഒരു സെൽഫ് ഇൻഡ്യൂസ്ഡ് EMF, ഒരു ഇൻഡ്യൂസ്ഡ് EMF ഈ ഇൻഡക്ടറിനെ ക്രോസ് ഡെവലപ്പ് ചെയ്യും. ദാറ്റ് ഇൻഡ്യൂസ്ഡ് EMF opposes the decay of the current. That induced EMF causes a sparking across the air gap. ഇവിടെയുള്ള എയർ ഗ്യാപ്പിൽ നമ്മൾ കീ പെട്ടെന്ന് അങ്ങ് വലിച്ചങ്ങ് ഊരുന്ന സമയത്ത് കറണ്ട് പെട്ടെന്ന് കുറയുമ്പോൾ ഇവിടെ ഉണ്ടാകുന്ന ബാക്ക് EMF, ഇൻഡ്യൂസ്ഡ് EMF, അത് ഒരു സ്പാർക്കിംഗ് ഉണ്ടാക്കും. അത് പെട്ടെന്നുണ്ടാകുന്ന ബാക്ക് EMF മൂലം ഈ എയർ ഗ്യാപ്പിൽ ഒരു സ്പാർക്കിംഗ് ഉണ്ടാകും. അപ്പോൾ ആ സ്പാർക്കിംഗ് ഉണ്ടാവണമെങ്കിൽ, ആ സ്പാർക്കിംഗ് ഒഴിവാക്കണമെങ്കിൽ നമ്മൾ എന്ത് ചെയ്യണം? ഇവിടെ റിലാക്സേഷൻ ടൈം കുറച്ചാൽ പോരെ. That is, to reduce the sparking or to avoid the sparking, we have to increase the relaxation time. We have to increase the tau. Tau increase ചെയ്യണമെങ്കിൽ എന്ത് ചെയ്യണം? നമ്മുടെ ഈ എല്ലിൻ്റെ വാല്യൂ ഒത്തിരി കൂട്ടിക്കൊടുക്കണം. ഓക്കെ, അപ്പോൾ ഈ എൽ വാല്യൂ, ഇൻഡക്ടറിൻ്റെ വാല്യൂ കൂട്ടിക്കൊടുത്തു കഴിഞ്ഞാൽ we can avoid the sparking. That is, to avoid this sparking problem, the L should be made large. Okay. Now, let us note down those points also. That is, this rapid decay of current results in large induced EMF across the inductor, which sparking across the air gap. To avoid this, the value of the inductor L should be made large. That is, at the time of breaking the circuit, the resistance of the circuit becomes infinity. Then resistance becomes infinity, relaxation time goes to 0. That is, a rapid decay of the current will be there. This rapid decay of the current results in large induced EMF across the inductor, which causes sparking across the air gap. To avoid this, L should be made large. Thus, the time constant tau of the RL circuit may also be defined as the time in which the current in the circuit falls to 1 by E of its maximum value when the external source of EMF is removed. By looking at this expression, we can define the time constant in this way. Time constant means the relaxation time in this way also. That is the tau, that is called the relaxation time, or the time constant, that is defined as the time taken in which the current in the circuit falls to 1 by E, that is 36.79% of its maximum value when an external source of EMF is removed. Okay, that also we can note on here is the time constant tau of a RL circuit may also be defined as the time in which the current in the circuit falls to 1 by E, that is the 36.79% of its maximum value when external source of EMF is removed. In this way also you can define your time constant or the relaxation time. Now let us plot the growth and decay of the current in the LR circuit together in a graph. That is our next aim. That is, we have the two equations. The growth of the current is given by this expression that we have derived in the last class, and the decay of the current that is given by this expression. Now if we plot these two graphs, the growth that will be of this form, it reaches its maximum value at a certain time, and let's say this is the growth, and the decay of the current that will be, just now we have seen approximately this will be the graph. Should be very smooth one. This is decay. Okay, fine. This is all about the growth and decay of the current in an LR circuit. Okay, thank you very much.